Hi, I'm Brad Garner, and I'm honored to speak with you about Roof Diagnostics Laboratory and our research. Roof Diagnostics is an independent research institute focused specifically on green roofs. We work worldwide, and my colleague Dr. Anna Zachrisson leads our European efforts. Our laboratory is in Culpeper, Virginia, USA, not too far from where I live in Washington, D.C. I'm going to start by showing you a bit of our laboratory, then show you some actual testing, cover briefly why we do this, and I have just enough time for a teaser of some hydrologic modeling. Most of our work the past few years is focused on water quantity, that is retention and detention, but we're looking forward to more work in water quality, such as nutrient mitigation, in the near future. Here you see the front of our research laboratory. Yes, this is a converted shipping container. In the foreground, you see a few green roof monitoring platforms. But let's start with a bird's eye view of the full compound. Roof Diagnostics rents this rectangle of land from Sempergreen USA, so we're right in the middle of a huge sedum farm. The shipping container lab is right in the middle. Notice a weather station on top. These rails are an extension of the lab. These are for moving cassettes in and out. We have about 24 cassettes, and you can see most of them here. These are 1.2 meters wide by 6 meters long, and each holds a different green roof profile. People always ask about the ramp. This was actually a mock-up from a Sempergreen and American Hydrotech project at the Kennedy Center in Washington, D.C. We continue to monitor the ramp's long-term performance. The bottom is a green roof, and the profile slopes upward to form a full 90 degrees as a green wall at the top. Finally, we have outdoor platforms, and that's where we'll start our tour. Most of these platforms are for monitoring long-term plant performance. Each contains a different profile, and they're all almost 8 years old. We should be able to finalize our study after 10 years of monitoring. A key part of the vegetation study is taking weekly photographs from the same location. Here you can see the legs of the quad pod we use to position the camera over one of the deeper, more diverse profiles. The few platforms at the far left are used for studying evapotranspiration. Here's a view of these platforms from eye level. And if we look down below, we see the scales and tipping buckets. All our hydrologic research uses industrial scales, or more technically, weighing lysimeters, for the most precise water measurements. We also measure runoff via dual tipping buckets behind the aluminum shields on the right. We measure temperature within the top, middle, and bottom of each profile and compare this against ambient air temperature. All this data is used for retention and evapotranspiration studies. I have to exercise restraint because there isn't time to get into every detail, but here's a graph of a single storm event comparing rainfall and runoff of the 4 platforms. We also have similar graphs for evapotranspiration, but evapotranspiration is a much slower process, so that graph is much longer. A key factor we're measuring is the crop coefficient of different green roof plants, particularly mixed sedum, and plants native to certain regions that might be used on green roofs. A lot more data is needed to precisely determine evapotranspiration in green roofs, particularly if we're going to engineer that value to its maximum. We now have similar platforms set up in Australia, with 3 more coming in the Netherlands, Germany, and Slovenia to cover a broad range of European climates. Our location on Sempergreen USA's farm in Virginia is actually ideal, because though at ground level, the land is open for several kilometers all around, resulting in hotter and windier conditions similar to what might be found on a roof a few levels above ground. So let's move on to those long cassettes that you see here at the top left. These are fairly large green roof specimens, so moving them requires heavy equipment. We intentionally chose to research large specimens, as we suspected small specimens might produce excessive size bias. Turns out we were right. We study retention and detention, and edge effect is well documented in retention. But in detention, size is even more critical. These 6-meter-long cassettes simulate the length of a typical flow path to a roof drain, which is an important factor to capture. We want data that reflects expected field performance as closely as possible. We measure the volume and mass of each layer within the profile, and this accounts for normal construction tolerances. So what types of green roofs do we study? In short, all. You're probably most familiar with what we refer to as the traditional green roof concept. These are usually built in place, but sometimes modular. These are still the most common. The sponge roof concept incorporates high retention materials, such as needled mineral wool. Then the purple roof concept builds upon that by adding detention or delay for peak flow control. The blue-green roof concept is also somewhat common, and it uses a reservoir or buffer layer below the green roof to provide detention on flat decks. We've studied more than these, but these are just the four primary concepts. For detention, our primary research tool is the rain simulator. This device is capable of simulating rainfalls from 10 millimeters per hour, which is just a mist, up to 200 millimeters per hour, which is a downpour. We can test its slopes up to 2.5%. By simulating these real-world conditions with fully assembled profiles, we get the best data. The setup includes a reservoir to pre-measure rainfall. This is at the top right. This is on a weighing glycimeter, noted throughout the drawing as WL. This is pumped to an overhead irrigation system to be delivered at a calibrated rate. Water lands on the green roof in the cassette. Water that flows out the bottom is metered as drainage, and water that flows off the top, if any, is metered as sheet flow. All data is saved at 1-minute time steps and stored in our cloud-based software, which also handles preliminary analysis to assist our hydrologist. So you might ask, what exactly are we researching here? So I'll step back for a moment. We all know that green roofs play a critical role in reducing annual runoff volume, providing urban habitat, cooling cities, and reducing energy use. We want to see more green roofs, but reducing total runoff volume is only part of the stormwater problem that big cities are dealing with. In the eastern US and throughout much of Europe, storms are becoming more intense, which is causing health and safety problems in big cities, mostly localized flooding and sewer overflows. If we zoom in, we can see there is a lot of rooftop space. In fact, about 40% of all land in a city is covered by rooftops. About another 40% is covered by pavement. And it's a lot harder to get pavement to provide any stormwater benefit, but we can do that with rooftops. And by stormwater management, we mean during small storms and big ones. Storms such as this cloudburst cause flooding, property damage, and sewer overflows, and they are becoming more common in a lot of cities around the world. So I hope that answers the question, what are we researching? We are researching how green roofs can actually be a big part of solving that problem. So here's the rain simulator at work. In this case, we simulated a 1,000-year storm. Not all our tests push the limits of green roofs like this. In fact, we're usually going up to about a 50 or 100-year storm, but why not start this off with a bang? So this test applied 200 millimeters of water to a 100 millimeter thick green roof profile in the course of just an hour, after applying 200 millimeters over the course of the prior 12 hours. That is a lot of water, but we have actually seen storms like that in just the past few years. In this study, we're studying surface damage and peak flow attenuation. I won't get into any specific test results here because there just isn't enough time, and those deserve not to be rushed, but I will just say that some profiles and some concepts perform well in these circumstances, and some do not. This is a very specific test of a worst-case scenario with no vegetation and a high degree of sheet flow. This was looking at surface damage, and in most of the profiles there wasn't any. We study extreme performance in our laboratory, and actually studying extreme performance is often a lot of fun. We test every aspect of a profile. This is looking at only the two bottommost layers of a purple roof concept profile. The chains that you see on top are just ballast to weigh down the lighter bottom layers, as they would always be under some weight, so it wouldn't be realistic to test those without any weight superimposed. The small probes that you see here are inspecting hydraulic gradient. That's the gradual curve of subsurface water that is highest farthest from the drain and then lowest at the drain. We often perform some of these manual experiments while we're determining what sort of electronic monitoring devices to invest in. Since extreme performance pushes the limits of green roofs, we do measure overflow events or sheet flow, and you've already seen some of that. We generally recommend designing to avoid sheet flow, which is avoiding an overflow event. But it's really important to study the phenomenon in order to understand it, prevent it, and manage it. To meter this separately, we usually use an apparatus, as shown. This collects drainage from the bottom as it flows under the edging, and then pipes surface runoff to a separate collection trough. It looks like this in section. Another interesting research project is testing the stormwater efficacy of green roofs in combination with solar panels. Yes, these are imitation solar panels here, but hydrologically they perform the same. We should finish this research sometime in 2021. The obvious challenge with this is the even distribution of water below the panels and managing concentrated flow at the drip line of the panels. So what do we do with all this data? A big part of what we do is education, primarily of other people within the green roof industry, often manufacturers of green roof systems. We work with several manufacturers to incorporate improved technologies into their product lines and to rely on a rigorous scientific process when assessing and communicating performance to regulators and potential customers. And modeling is a huge part of that. We're currently using several different models. So far, no model has been perfect, as some handle dry to wet conditions better, and some models might be better suited to phenomenon in different green roof concepts. We do a lot of comparing model goodness of fit. The graph at the top shows an overlay of 2 different SWIM models and observed performance for 11 event data series from the rain simulator. SWIM is a modeling software produced by the US EPA, and it is the foundation of several private labeled modeling packages used worldwide, including several throughout Europe. We run several calibration models to determine parameters and then validate these models using the same parameters on different data sets so that we can compare performance and determine which models and which parameters are the best fit. This also allows us to provide regulators with useful data such as sensitivity analyses, so that it's clear which parameters require the most careful scrutiny in permit applications. We've done this so much, we've even been able to develop a quick methodology for interpreting hydrographs to assess if a certain profile even warrants detention study, and we can tell that after just a few tests. We've run nearly 1,500 tests in the rain simulator, and each one falls fairly neatly into one of these hydrograph signatures. But we're not done. We are expanding. Our first expansion was technological. We operated the lab manually for over 2 years, and last fall we built algorithmic controls for the lab. We basically enter a profile, slide it into the lab, and tell the system what to test for, and the lab runs and reruns tests as needed until the tests are complete and correct. This allows the lab to operate 24/7, including holidays and weekends, and test consistency has also improved. The second expansion is physical. Here's the lab as you've seen it so far. Last month we started construction on an addition. Here you can see the outline of the new work, including some new interior space. And most significant of all, a 150 square meter rooftop for studying detention performance, specifically the delay of water after the green roof is wet and the resulting peak flow reduction. Currently the roof is just full of water while we check for leaks until the green roof is installed, but that should be completed in March or April of 2021. All the water will drain to this tank, which is also on scales or weighing glycimeters. The tank is sized to hold 150 millimeters of rainfall from the roof, and this will be measured at a fraction of a millimeter at 1 minute time steps. This will be the same precision as our rain simulator, just a much larger size that is similar to a single drainage area on a commercial roof. This work should validate a lot of our research in the rain simulator. Further, the new space below allows us to expand soil and water quality research, which are particular areas of expertise for my colleague, Dr. Anna. So to recap, Green Roof Diagnostics researches retention and evapotranspiration and plant performance on all sorts of green roof systems. We also simulate monster storms to study detention to protect our cities from those large storms and green them and cool them at the same time. We model all this work so that you can use it. And we're here to support the green roof industry with rigorous science. Thank you all so much for your time. I hope this was interesting to you.